Right, welcome back everyone to our afternoon session. We've got two speakers, followed by a comfort break, and then a panel discussion with all our speakers from 3 o'clock to about 3:40. So another interesting session to come. So first of all, I'd like to welcome Dr. Michael Byrne, who's a climate scientist based at the University of St Andrews and the University of Oxford, and he is working on climate dynamics, and he's going to speak about, well, extremes, storms, floods, and extreme weather. So, Michael, over to you.
Great. Well, thank you very much, David, for the introduction, and thank you to the organizers of this really great event. Thanks for the opportunity to speak today. So my name is Michael Byrne. I'm a climate scientist based at the University of St Andrews and the University of Oxford, where I lead the Climate Dynamics Lab. And in the Climate Dynamics Lab, we use a combination of theory, computer models, and observations of the Earth system to address questions including why does land tend to warm more than the oceans as we change the climate? What processes control the size of the tropical rain belts, and how might the warmest days change in the future relative to the average day? And I'll get to some of our recent work on that last question towards the end of this talk. So in my talk, I'm going to focus on extreme weather in a warming climate. And in particular, I'm going to try and emphasize what we can understand about how extremes are changing and will continue to change based on very basic physics principles. And I'll also point out some of the key unknowns when it comes to extremes and how they're changing, and point to some of the efforts underway in the climate science community to try and overcome these uncertainties. Okay, so I probably don't need to emphasize this point too much, but why should we care about extreme weather in a warming climate? So data from Munich Re, the reinsurers, tells us that global damages from weather-related disasters totaled $212 billion last year and are increasing year on year. And we expect 2021 to surpass even that amount. We all remember the devastating floods from July in Germany, which killed over 180 people. At the start of September, New York City was completely inundated with rain originating from the remnants of Hurricane Ida. And then earlier in the summer, so towards the end of June, there was this really remarkable heat wave in the Pacific Northwest region of North America. And one town was particularly badly hit during that heat wave, the town of Lytton in British Columbia in Canada, which had an exceptional few days towards the end of June. It broke the all-time Canadian temperature record on 3 consecutive days, so June 27th, 28th, and 29th. And then on the 30th of June, the town of Lytton caught fire and was basically razed to the ground. So it's hard to imagine a more stark story to illustrate the effects of extreme weather and potentially how those impacts are changing as we change the climate. Okay, so in my talk, I'm going to focus on two types of extremes, heat extremes and wet extremes. And first, I want to kind of orientate everyone with what our climate models suggest will happen to these extremes as we warm the climate. So here I'm showing a figure from a recent report from the Intergovernmental Panel on Climate Change focused on extreme events. And what's shown here is the probability of having either a hot day, so in blue, that would be the hottest day every 100 days, or in red, the hottest day you might experience every 1,000 days or every 3 years, and how the probability of having one of those days changes as we warm the climate on average along the bottom axis. So the way to read this figure is that at a global warming of 1 degree, which is roughly where the world is right now, the likelihood of experiencing a 1 in 100 warmest day is about 2.5 times what it was in pre-industrial times. If we look at more extreme heat days, those are those red curves there, and these show the likelihood of experiencing a 1 in 1,000 So I was discussing this figure, which is from the IPCC report, and basically showing that as we warm the climate on average along the bottom axis, the likelihood of having these hot days or very hot days increases very rapidly. And similarly, if we look at a similar plot, but for the wettest days, so the 100, but the 1 in 100 wettest day in blue, or the 1 in 1,000 wettest day you might experience in red, as we warm the climate, we see that the likelihood of having these very wet days increases as climate warms quite steadily. And I should mention that each of these lines is a different climate model. So there's some degree of uncertainty between different climate models regarding how the likelihood of these events will change, but they're all pointing in the same direction, indicating more likely to have hot days and wet days in a warmer climate. So really the aim of my talk today is to try and explain using basic principles from physics and how we can understand these increasing likelihoods of hot and wet days. Okay, so I'll talk about why are these extreme events becoming more likely? What can basic physics tell us about these trends? But maybe most importantly, what do we not yet understand? Where do the uncertainties lie? And is there potential for surprises when it comes to extreme events? And I'll argue that there is likely potentially to be some surprises when we think about extreme events in a warming climate. Okay, so first I'll talk about heavy rain events or wet days in a warming climate. So why are wet days appearing to get wetter? And I choose to start with discussing wet days rather than hot days, because at least in my mind, the science is in a sense more straightforward to understand. Okay, so why does warmer typically mean wetter? So before I try and answer that question, first, we need to talk a little bit about how rain forms. So my apologies, this is meant to be an animation, but with the switch to PDF, you'll just have to imagine it animating in front of your eyes. So to understand changes in wet days in a warming climate, we think about how rain forms. So rain basically forms from taking air near the surface that contains lots of water vapor and moving it upwards. Now, water vapor is a gas, you can't see it, but it's in the air around us. And when you take air and move it upwards, we cool the air and cause that water vapor to condense into liquid water, which forms clouds and eventually rain. So that's what we basically need to do to form rain. We need to take air from near the surface and somehow move it up in the atmosphere where it's colder and where we can cause it to condense. Okay, so we can write an equation to relate how much rain we get as a function of how much water is in the air multiplied by the speed at which air is rising. So this is an approximate, but a simple but approximately correct equation that relates rain to the amount of water vapor in the air and how fast the air moves upwards. So with this equation, we can play some games in our mind, and we can say, okay, what would happen to the amount of rain if we increase the amount of water vapor in the air? So it's fairly straightforward that if you have more water vapor in the air, you would expect to get more rain. And similarly, if we increase the speed at which we move air upwards, we would also expect to get more rain. Now, the key to understanding how heavy rain events or wet days change with climate change, the key to understanding that phenomenon goes back more than 150 years to these two chaps on the left, Rudolf Clausius and Benoit Clapeyron, who together are credited with the Clausius-Clapeyron relationship, which is a result from thermodynamics that has been around for a long time, as I said. And basically what the Clausius-Clapeyron relationship tells us is that warmer air can hold more water vapor. And when we think about Earth's atmosphere, the Clausius-Clapeyron relationship tells us the same thing, that a warmer atmosphere can, and in fact does, hold more water vapor. So the warmer the atmosphere is, the more water vapor it can hold. And we can quantify that quite readily. It's quite a steep increase in the amount of water vapor air can hold as you warm it up. So for every degree that you warm the air, we tend to see about 6 to 7% more water vapor in the air. And this is the key bit of basic classic physics that enables us to understand changes in heavy rainfall events as climate warms. So the basic prediction that this physics would tell us is that if we increase the amount of water vapor in the air by 6 to 7%, and if for now, and a classic physicist assumption is, let's assume for now that the speed at which air moves up doesn't change, then our prediction is that the amount of rain that we get would be 6 to 7% more per degree that we warm the climate. Again, so basic physics giving us this prediction, and we make this assumption that the speed at which air moves up doesn't change much as we change the climate. So let's see how our very simple prediction actually does when we look at projections of extreme rainfall in a warming climate. So what I'm showing here is a figure from a paper by Paul O'Gorman a few years ago, showing the sensitivity on the vertical axis in units of percent per degree warming of the 1 in 1,000 wettest day. So the amount of rain you get on the 1 in 1,000 wettest day when you look into a future climate using climate models to project that future climate. And what we see is that the changes in extreme rainfall, which we see in climate models, at least in the extratropics, so poleward of about 30 degrees of latitude, so towards the left and towards the right of this figure, broadly line up about 6 to 7%. So what that tells us is that this very simple prediction of how rainfall should change in the future follows more or less the prediction based on this Clausius-Clapeyron relationship, which we've known about for over 100 years, I should say. So if we're thinking about Scotland and how heavy rainfall events should change in Scotland in the future, it's pretty straightforward. We expect about 6 to 7% more rain in these events per degree that we warm the climate. Now that's in the extratropics, but if you look closer to the equator, closer to 0 degrees latitude, we see that there's huge uncertainty in what different climate models project in terms of extreme rainfall events in tropical regions. So some models predict more than 30% per degree warming increase in these extreme rain events, whereas other models down at the bottom predict no change. So you could either have a catastrophic increase in extreme rainfall or no change. So there's huge uncertainty in the tropics. And the reason for that uncertainty in the tropics is because of the dynamics of heavy rainfall events in the tropics. So if we think about the tropics, when you have a heavy rainfall event, it's typically associated with a thunderstorm. And a thunderstorm is a small storm which has fast moving air in its core, which drives strong condensation and strong rainfall. But unfortunately, we don't have a robust theory for how quickly air should move up in the core of a thunderstorm, let alone whether that velocity of air in a thunderstorm should become stronger or weaker when we warm the climate. So we've nothing to rival the Clausius-Clapeyron relationship when it comes to understanding changes in this speed at which air is rising in rainfall events. And this lack of a theory for ascent speed in the tropics is compounded by the inability of global climate models to resolve these heavy rain events. And that together, this lack of a theory and some deficiencies in the models, particularly in tropical regions, lead to uncertainty. So what do I mean when I say that global climate models can't resolve these storms? Well, so here's a schematic of a global climate model. So when we model the climate, we divide the atmosphere and the ocean up into little boxes of finite size, and we simulate things like temperature, wind speeds, moisture on the edges of those boxes. And the current generation of global climate models have boxes with sides that are about 10 kilometers in width, or maybe a bit more than that. So any phenomenon in the atmosphere that occurs on spatial scales of less than 10 or 20 kilometers, so a cloud or maybe some thunderstorms, cannot be actually explicitly simulated by the model. Instead, the model needs to parameterize those effects, or in other words, tries to predict the dynamics of an individual thunderstorm, which it cannot resolve based on what it can resolve on the broader grid box. So as you can imagine, this parameterization process is very difficult to do, and there are large errors associated with it. So unfortunately, global climate models cannot yet resolve these storms in the tropics, and this is part of the reason for the uncertainty in how extreme rainfall events will change in the future at tropical latitudes. I just want to mention that there are some really interesting efforts in climate science to try and overcome these deficiencies in the models, or to try and overcome this computational barrier. And broadly, there's two strategies that are gaining traction. The first strategy says, okay, we have these coarse resolution models and we want to make them better, but we acknowledge that we will be stuck with these coarse resolution models for quite some time. But we can try and make them better by improving their parameterizations of things they can't explicitly simulate, by using the abundance of satellite data and some limited domain high resolution simulations to better train our coarse models to predict things like thunderstorms better. So that's one avenue of research that's ongoing. And the other broad approach is quite different, and it says that as a global community, we should really be throwing all available computational resources to accelerate the resolution of these models, make them more and more powerful, so that we can quickly reach the point where we can start resolving these tropical thunderstorms in global climate models. And if we can, the idea being that if you can explicitly simulate these storms in a model, you can make better predictions. So this idea has been termed a CERN for climate change, in analogy with CERN, which is the large international effort focused on advancing understanding of fundamental particle physics. And there's a lot of lobbying going on to try and divert more and more of the world's top-end computing resources to climate science. So there are some of the efforts that are ongoing. Okay, so those are that was my discussion of kind of heavy rainfall events in a warming climate, and what can we say based on basic physics, so Clausius-Clapeyron relationship, and what don't we know, which is really related to these ascent speeds in thunderstorms and what controls them and how might those change in a warmer climate. Now I want to move on to extreme temperatures in a warming climate and think about why are hot days becoming more frequent. Okay, so one way which I like to think about the likelihood of having a hot day and how that might change as we warm the climate on average is to think about a probability distribution of temperature. So this is a hypothetical probability distribution of daily temperature. So the way to read this figure is you say, okay, this shows the likelihood of having a given temperature on a given day in some part of the world. So the average day is broadly speaking the center of this probability distribution. The likelihood of having cold days are on the left and hot days are on the right. So in these tails at the left and right of the temperature distribution shows the likelihood of having either a hot day or a cold day. Okay, so basically the likelihood of having a hot day, which I define here just for illustrative purposes to be a day above 25 degrees Celsius, is proportional to the area under this curve above 25 degrees. Okay, so if we think about warming the climate on average, so I mentioned earlier that the climate has warmed about 1 degree since pre-industrial times. So if we think about warming the climate and shifting this probability distribution to a warmer temperature on average, what happens to the likelihood of having a hot day, say? So if we shift this whole curve to the right, a very straightforward consequence of that is that we expect more hot days, so more area under the curve to the right of 25 degrees, and fewer cold days, so less area under the curve to the left of 5 degrees C, which is a cold temperature I've defined here. So that's a very straightforward consequence of shifting this distribution to a warmer temperature on average. Now, what I've done when I kind of did this kind of thought experiment is I assumed that the shape of this distribution didn't change. I just took the distribution as it is today, shifted it 1 degree to a 1 degree warmer climate and said, what does this tell us about the likelihood of having a hot day or a cold day? And if we kind of do that and we assume the shape doesn't change, then more hot days, fewer cold days are very straightforward consequences of global warming. But when we make that assumption of shifting this curve but not changing its shape, basically what we're saying is the day-to-day variability in temperature should broadly be the same in a 1 degree warmer world compared to what it is today. We're kind of saying the temperature variability doesn't change very much. So this kind of shift in the distribution implies that basically the average temperature, the temperature of a hot day, and the temperature of a cold day, they all shift forward by 1 degree C. But you could imagine that as you warm the climate, you not only shift this distribution to a warmer average temperature, you also change its shape. So if we even subtle changes in the shape of this distribution, either on its warm tail on the right or on its cold tail, can have big implications for extremes. So here I've done a subtle change in shape of the distribution when you move to a warm climate, and that might mean that the hottest day might actually warm quite a bit more than the average day. Or you can imagine a change in the shape of the temperature distribution on the cold side, meaning that the coldest day each year might actually become colder despite the average temperature warming up. So these subtle changes in the tails of the temperature distribution are really a focus of climate science at the moment, and trying to understand the implications of changing these distributions for those extreme events. So I want to now talk about, is there potential for surprises like a colder day, the coldest day each year becoming colder despite climate warming? Are those kind of surprising or curious possibilities, are they likely to happen when we in a warming climate? So first, I'll talk about the likelihood of having a colder day in a warmer climate. So a recent occupant of the White House was quite perplexed by this idea. So a few years ago, he wrote, he was somewhere in the Midwest, and he said it was minus 60 degrees, the coldest temperature ever recorded. What the hell is going on with global warming? Please come back fast. We need you. And this idea that somehow global warming might be consistent with colder winter temperatures is not, is actually caught hold in the media, and is a hypothesis that's out there that in some way global warming and colder winters are consistent with one another, even though it's a curious idea. So what is that hypothesis based on? So the idea that warmer climate might mean colder extremes is an influential hypothesis. It's been around for around 10 years or so, and it relates to the dynamics of the jet stream. So here I'm showing a map of the jet stream, which is this core of strong winds that move from west to east in mid-latitudes, about 5 to 7 miles above Earth's surface. And this jet stream has undulations and waves in it, which strongly determine the high and low pressure systems that dominate our weather in this part of the world. Now, the idea behind this hypothesis is that as the climate warms, that affects the dynamics of the jet stream. And in particular, the hypothesis goes that the jet stream slows down and becomes wavier as you warm the climate. And a slower jet stream and a wavier jet stream means that these cold masses of air, so you can see one here coming down from Greenland, which deliver the cold weather in mid-latitudes, that when the jet stream is slower and wavier, those cold masses of air might be more likely to linger in place for longer and deliver colder snaps of weather despite an overall warming climate. So why might you expect the jet stream to slow down as you warm the climate? So here I'm showing temperature changes on the left, surface temperature changes on the left, and we see that northern high latitudes, so the Arctic Circle basically, is warming more than twice as fast as the rest of the world, leading to a large reduction in sea ice, which is shown on the right. And the idea is that this rapid warming of the Arctic affects the equator to pole temperature gradient and the equator to pole pressure gradient, which ultimately drives the jet stream, and that this might cause the jet stream to slow down and to cause these weather systems kind of remain in place for longer. So I won't go into any more detail about this really fascinating hypothesis. Suffice to say that it's being hotly debated in the scientific community. So despite this being quite a strange idea that a warmer climate might deliver colder snaps during the winter, there is some support for that hypothesis, but it's being strongly debated. So I'd suggest to watch this space. And I'm just keeping an eye on the time. So due to my technical difficulties, I think I'm running out of time. So I'll just quickly jump over the last bit of my talk in the interest of time, and I'll go to my conclusions. And I'll just say that so very hot days and very wet days are becoming more frequent as climate warms, and this is challenging infrastructure and societies. But within those broad trends, there is potential for surprises. So there is an active area of research looking at whether we expect cold days to get colder despite a warming climate. And there's also research, which I glossed over at the end, suggesting that the hottest days each year might be warming more than the average day, which is not good news for a variety of reasons. So what's the state of the art when it comes to trying to predict extreme weather? And there's a lot of effort using deep learning, artificial intelligence, and exascale computing, along with basic theory, to try and narrow uncertainties in how extremes will change in the future. And the goal, which many of us are working towards, is to get reliable, actionable information on extreme weather risks to help individuals and societies to prepare for and adapt to future climate warming. So with that, I'll stop sharing my screen, and thanks again for the invitation to speak.
Okay, thank you. I'm going to turn to a question for Michael now, actually. So Vicky Ingram has asked, do you think we should be using supercomputing and machine learning on ever smaller scale climate models, or use the expertise on solutions? To put it flippantly, would we be better off applying computing knowledge to how we can adapt or mitigate rather than telling us slightly more accurately and confidently just how screwed we are?
Thanks for the provocative question, Vicky. So how would I answer? I think I would approach that question in two different ways. From a practical standpoint, is the information that climate scientists that are providing now, is that good enough for mitigation and adaptation? I guess partly it is. You know, as I said, warmer days are becoming more frequent, wetter days are becoming more frequent. That's actionable information, but the information isn't that good, really. So if we take just one number, which is a number that climate scientists love to talk about, which is the climate sensitivity, so how much warming you get per the amount of CO2 you put in the atmosphere, our best estimates of that climate sensitivity are about 2.5 degrees Celsius to 5 degrees Celsius. That's the likely range. So it's a factor of 2 difference. So if you talk to an engineer and say you need to build a flood protection system for either, you know, a rain event of this magnitude, or maybe for a rain event of twice that magnitude, I think that's a huge amount of uncertainty for us to wrangle with and practically deal with on the adaptation side. So I think, you know, a certain degree of adaptation and can be planned for based on what we currently know, but the uncertainties that are there are still really large as far as I'm concerned. So that's kind of on the practical side. In terms of, you know, whether we should be devoting supercomputers and machine learning and theoreticians to better understanding the climate system, I think I would step away from you know, as a climate scientist, it's very difficult to step away from the very practical aspect of our work, which is trying to inform the world, you know, what's happening, what's going to happen. But I think if we can do that, I'm fascinated by climate as a phenomenon, you know, how the atmosphere works, you know, what contributes to a very hot day, what are the processes. So I think from a fundamental science standpoint, and the Nobel Prize in Physics being awarded to climate scientists yesterday, I think there's great validation for looking at climate for the practical purposes of preparing society, but also climate in itself is a fascinating, complex system that we all live in every day, and it's worth studying for intellectual purposes, for academic purposes, for curiosity purposes. And so I think for 2 reasons it's worth keeping going with the climate science.
Thank you. I mean, I suppose from my point of view, it's very interesting to be looking at extremes from the basics of the physical contributions that are being made to extremes. And I don't think that's been done as much as it ought to have been done. It's been taken as a output from a climate model, but without the underlying thinking about, well, what actually contributes to extremes. So I think that's been very, very useful. You didn't mention wind. Have you investigated changes to variation in wind speed distribution, as this could have an impact on wind turbines and stable supply and energy from them?
Sure. So yes, it's a good point. I didn't talk a lot about winds, and the reason I didn't talk much about winds is that basic physics isn't getting us very far in understanding how the mean winds or day-to-day variability with winds will change as we warm the climate. There's a lot of research going on in that space. So we talk about a potential shift poleward in the jet stream. We talk about an expansion of the subtropical dry zones into the Mediterranean region. But none of these effects, I can't explain any of these effects to you in terms of very basic physics. These are largely derived from climate models with some supporting theory. But really, the aspects of climate change science that we are very kind of confident in are the thermodynamic aspects. So temperature changes and related phenomena like changes in the amount of water vapor air can hold, which relies really on the temperature. But on the dynamics side, and by dynamics, I mean the winds, there's really a lot we don't know, actually. And that's kind of a big frontier in climate science, in my mind, is getting a better understanding basically of how winds will change.